Okay, we're hot on the trail of the moment of inertia of the Earth in its rotation about its axis. The integral is this, and we just have to perform the integration, which is not going to be bad at all. Okay, so putting the integral down again, we have the integral from 0 to pi, from 0 to 2 pi of what? That's going to be 12 rho cubed minus 9 rho to the 4th over r. That's going to give us 12 rho to the 4th over 4, which is 3 rho to the 4th, minus 9 rho, the integral of 9 rho to the 4th, which is going to be, the integral of rho to the 4th is going to be rho to the 5th over 5, so we're going to end up with 9 rho to the 5th over 5r, evaluated between 0 and big R, and then times the integral of sine squared phi d rho. We don't have d rho, we have d theta d phi. I'll fix that. Next time I make a mistake, I'll come back and fix that one too. Okay, so this expression becomes simply, it's going to be 3 rho to the 4th minus 9/5 rho to the 3r to the 4th minus 9/5 r to the 4th. Now let's see, 3 is 15/5, 9/5 is going to leave us 6/5. So I think we're going to end up with simply 6/5 r to the 4th. That's actually going to be a constant come out in front of the integral because r's radius of the Earth just constant. We'll leave it inside the integral for the moment. So we're going to have the integral from 0 to pi, but I'm going to go ahead and integrate d theta from 0 to 2 pi. And not 2 theta, it's going to be just plain old 2 pi. So there's my next mistake, so let me fix these two real quickly. Okay, I'm not sure I did a whole lot of good on that theta. It still looks pretty bad, but we can see what it is. And this becomes 2 pi, not 2 theta, or whatever I wrote. And then that's got to be integrated with respect to up, sine squared phi, integrated with respect to phi. Okay, now I think I've got everything. Remember, the integral from 0 to 2 pi of d theta is just 2 pi. This evaluates just to this, which is constant. So we end up with 6/5 r to the 4th times 2 pi. Multiply that out. Of course, we're going to get 12 pi over 5 r to the 4th times the integral from 0 to pi of sine squared phi d phi. Now, in recent examples, we've integrated the sine squared of a variable, and we recall that that's going to be like a 1/2 sine cosine, negative 1/2 sine cosine, minus a theta over 2, I think, and the sine cosine having a factor of sine is going to be 0 at both 0 and pi over 4. So we're just going to get theta over 2 evaluated between 0 and pi, and that's going to give us pi over 2. So without doing all the details and still writing everything out separately for the moment, our integral on rho gives us 6/5 r cubed. Our integral of d theta between 0 and pi over 2 gives us 2 pi. Our integral d phi from 0 to pi gives us pi over 2. And now we can multiply all this out. The 2 divides the 2, so we're still going to have a 6 here. 6/5 pi squared times r to the 4th. That's the moment of inertia of the Earth about its axis. As usual, my solution bothers me. I suspect there might be an error because I don't have the right power of R here. The moment of inertia of a uniform sphere is 2/5 mr squared. That's easily derived by a very similar integral with a constant mass density. Mass density of the Earth is not quite constant, but what we get should be at least comparable with 2/5 mr squared. The mass of the Earth is what? We found it to be, according to this model, the density model that we're using here, was 7 pi r cubed. So that 2/5 the mass of the Earth times r squared would be 2/5 of this times r squared. That would give us an r to the 5th. And that equals, well, 2/5 times 7 is 14/5. And that would be pi times r to the 5th. Now 6/5 pi squared is close enough to 14/5 pi. If pi is about 3, then 6 pi is about 18. We'd have then about 18/5 pi left if we let one of the pi's equal 3. So don't have a big problem with that. Although I would expect this multiple to be a little bit less. In other words, the mass of the Earth is not uniform. It gets less as you move toward the outer surface, and r gets bigger, r not being linear, and so forth. You have more mass concentrated toward the center. Should give you a lower moment of inertia than for a uniform sphere. Let's not worry about that. Let's worry about what's going on with this r to the 4th and r to the 5th. Okay, after a quick look, I see the problem, and it goes back to the original expression that we had for the moment of inertia, where I didn't square my radius. I didn't square my distance from the axis. So the entire integral is wrong. What I've integrated is mass times distance from the axis, which would be useful if, for example, we were trying to find the center of mass of half the Earth. We could let theta go from 0 to pi instead of 0 to 2 pi, so we'd only get 1/2 of the Earth, and we could calculate the center of mass of half the Earth. That isn't a particularly useful calculation, but could be done. We wouldn't get the center of mass, we'd get the torque. We'd divide that by the mass of half the Earth, and then we would find the distance of the center of mass of the hemisphere. If we cut the Earth in half, the hemisphere that we'd get lost track of my entire sentence, but we'd be calculating the moment of inertia, the center of mass of that hemisphere. Divide this integral from 0 to pi here by the half the mass of the Earth. Now, that wouldn't be useful at all. If we cut the Earth in half, it would collapse on itself and form a smaller sphere, but that could be an interpretation of our integral in any case. So to get the correct moment of inertia integral, we're going to have to square this term. So that's the radius squared, not the radius, and that's going to make a difference. It's going to give us a 4th power here and a sine cubed here. So this power is going to turn into 4. This power is going to turn into a 3.